Good afternoon, everyone. I hope that you guys are having a good day. Today is the 2nd of March, and we are going to jump back into proteins and enzymes. But before we do, I was going to take a minute to pull up our class calendar just to show you where we are in the semester and kind of what's on the agenda. So, let me share my screen. Do, 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 do. Right. So 4375, Chem 4375, biochemistry. And let me get my all that stuff. Okay, so we are looking at this is our 12th class meeting, March 2nd, 2026. Sorry. And what we've got on the horizon is we don't have any exams before spring break. Um, we'll just be kind of going over new topics and new content, talking about enzymes. And this is really a pillar of understanding your first semester in your first biochemistry class. If you go on to take metabolism, which I strongly advise because it's a great class, and it's lots of application of this. We're going to get into some metabolism, but not go nearly as deep as you do in a full semester's metabolism class. If you go on to medical school, PA school, any sort of professional school, you will spend an entire, well, I think in medical school, your semester is basically broken down into like 6 weeks or something, on a very accelerated plan, not plan, but on an accelerated timeline. So you'll spend a lot of time on this, but it's always good. And I've always heard positive things about having taken a metabolism class prior to, medical school or PA school or whatever. So our next exam, though, is going to be on April 1st. And what I wanted to bring up was I probably have to do some travel due to a funeral that I have to attend. And so on March 30th, chances are I'm going to have that be an asynchronous class meeting, so not a meeting. It's going to be pre-recorded. And then what I was planning on doing was on, I guess that would be March 31st, I would have a lecture, or sorry, office hours to kind of offset the fact that I didn't have office hours on the 30th and that I didn't have a class meeting on the 30th. But that right now is what I have planned. I just wanted to bring that to your attention. Somebody sent me a private message of my condolences. Thank you. I appreciate that. That's very thoughtful. But if anything like that comes up, I really I will always want to get ahead of it and let you guys know as soon as possible. Especially, I really don't like to do that. Right before an exam because I know that that's when lots of people have questions. And so then it's like, hey, I got questions for you. Um, and I don't have a class meeting. That's kind of like, who am I supposed to ask questions to? At any rate, with that in mind, um, I just wanted to bring that up to you guys and let you guys know that in advance. I think that, like we did with the last exam, this class date, so the Thursday after spring break, will probably be the last class date of new material for exam number two. So that will kind of make it a little bit easier. You have that weekend to um, process that information. But anyway, if anything like this comes up, if there's any unexpected change of schedule, I'll let you guys know as soon as possible. But in the meantime, do you have a coworker who we can go to with classes? Um, yeah, sure. Well, okay. Do I have a coworker we can go to with questions that you can get some time just for me and my family? Don't worry about me. And I'm not saying that in like a martyrdom way. I'm all right. It was for whatever it's worth. It was my wife's grandmother. Um, and she was a family member. I love her. She was great. But it wasn't to put it, I don't want to sound cold, but it was kind of there's a lot of runway people. We anticipated it. So I have no, please don't hold questions because you're like, ooh, he's going through a tough time. I'm all right. I appreciate the concern though. And so yeah, if there's other faculty members you want to talk to, there's a couple of other people who teach this class, and so you're welcome to ask them. Um, and I'll have to clear it with them that they're ready to take on questions from other students. But you guys, if anyone has the notion that you're like wasting my time or occupying too much of my time, please don't have.
Yeah. You only need to care about where.
I'm sorry, Lou, you were unmuted for a second. Don't worry about that. I'm doing all right. And um, after all, you guys are my job. Helping you learn biochemistry is part of my job. So I'm glad to do that. All right. So proteins and enzymes. This is part two. And the what I'm doing here with respect to proteins and enzymes is I'm casting a broad net. And then after you have a little bit of a broad assessment and understanding of these two topics, we're going to go deeper into each one of them. So we've gone into methods or models for enzyme catalysis, for example, last time, or models for reactions. And if anyone can't see what I'm writing on the screen, please let me know. But in the chat, I'm going to go ahead and assume that you guys can see that big letter E, enzyme. Can everyone confirm that they can read that all right with a 1 in the chat? Lou, do you have a question? Well, I'm going to go ahead. Oh, okay. All right. Okay. Yeah, I had someone send a message earlier that they couldn't read my screen, and I was like, don't worry about it. I think that person was watching the lecture on their phone, which yeah, that can make it a little bit more difficult. So we are going to jump back into hemoglobin, myoglobin, HB, MB, hemoglobin versus myoglobin. These are two proteins that serve the function of being O2 binding proteins. So they bind oxygen, and what they do is they just kind of hold on to it until they don't need to. So hemoglobin is going to bind oxygen and it's going to transport it to another part of the body. So it binds and moves it. That's what hemoglobin does. Myoglobin binds and releases. So essentially, releases. Essentially, hemoglobin does that same binding and releasing, but myoglobin, what makes it different is that myoglobin doesn't move it. No movement. So myoglobin stays in the tissues, whereas hemoglobin transports or moves all around your body. Last time, what we were talking about was we were talking about oxyhemoglobin versus deoxyhemoglobin. So the oxygenation of heme and the color of blood. Now, this right here, this structure right here is one of those structures that I think is, I've seen they both bind to O2, correct? Yes, that is correct. Thank you for asking. That was a private message question. These both bind to O2. They do. I'm happy that you brought that up because I do want to bring one thing up that is an important detail. Hemoglobin binds for O2, and myoglobin binds one O2 molecule. So that's the biggest difference that's not related to their function and movement. It's the number of oxygens that they bind. The structure of them is also different. Hemoglobin is a tetramer. Myoglobin is a monomer. Now, let's look at this right here. So this is the oxygenation of heme. Heme is our prosthetic group. And what this is asking us about is, well, it's relating heme and whether or not it binds oxygen and how that impacts or is related to the color of blood. So what this says is the binding of O2 to the Fe2 heme complex, alters the electronic state of the complex, changing that color. So the electronic state of this O2 plus heme plus Fe2 plus alters that electronic state. Now, the result of this is that venous blood is dark purple, whereas scarlet blood is, your arterial blood is scarlet red. So our deoxygenated blood is that venous blood, and our oxygenated blood is our arterial blood. So oxygenated. Now, these two, so this graph over here on the right-hand side shows our relative absorbance and wavelength. Now, these two peaks correspond to the oxygenated hemoglobin and deoxygenated hemoglobin. So what I want you to think about what that is HB protein plus heme plus Fe2 plus O2. Deoxygenated hemoglobin. Well, that's hemoglobin, HB, plus heme plus Fe2 plus, oh, 2 plus, and I'm just going to say less O2. And the reason that I'm saying less O2 is because when it comes to hemoglobin and its release of oxygen in the tissues, I don't want you to think about it as what hemoglobin does is it binds 4 oxygen molecules, goes to a muscle tissue, and releases all of them. There's almost different variations of it. So if you imagine hemoglobin returning to lungs, the alveoli within the lungs, you might have one hemoglobin with one O2 bound. You might have another one, HB plus 2 O2. You might have another one with 3 O2 bound. So I want you to think about this as a population of hemoglobin proteins, all of which have released a different number of oxygen molecules at the muscle tissue. Okay, so this right here, this return, this deoxy form is going to be kind of a mixture of hemoglobin proteins that are relatively deoxygenated. Now, this graph is showing that we have two peaks for oxyhemoglobin. Those two peaks are around 540 and about 500, and I'll call it about 585 nanometers. But for simplicity, I'm just going to circle it around 580 and 540 nanometers. Whereas our deoxyhemoglobin, that has a peak and lower points at around 540 and 580, but it has its peak at about 560. So these absorbances are how, if you have an Apple Watch, you have a Garmin, if you have a pulse oximeter, that's how this works. It gives you your assessment of essentially how oxygenated your blood is. And typically, if you go to the ER, if you go to, I think now it's just a part of any sort of doctor visit, they're going to measure your pulse or your blood oxygenation, and provided that you don't have any sort of what's the word? Breathing breathing issues, it's going to be about 95% or higher. I'm not trying to flex on anyone, but last time I got mine measured, it was like 98%. I think that's probably like clinically normal. Okay, so now what has to happen for this is we've got to have that iron 2 plus to bind to O2, and that iron has to be in the center of heme. Now I want to come back to this figure right here in the upper left-hand corner. That figure is one of those figures that you see in a textbook and you don't really think too much of it. Or I think that it's just kind of in there as like, hey, here's also another figure of this. What I want you guys to do is I want you to, not for the purposes of a learning objective, but just for processing the information, this green kind of region is representing our heme. The blue and the other blue, the blue up top and the blue down below, that represents histidine. 96, 98 is normal. If you have COPD or other respiratory issues, 90 to 96 is allowable, but not super concerning. Thank you very much, Emily. That's awesome. Um, yeah, I know that that's something that it's whenever I had my first kid, there's these tools or these little things that you can get for babies. You put them on their feet and it can monitor. It's a pulse ox and you can get them at home or for your home and it gives you this alarm on your phone that's like, oh my gosh, your baby's blood oxygenation is this. And it's kind of a, I don't know, just a little aside. Whenever somebody has a baby, they're terrified. Or at least I'll speak for myself. I was terrified. I didn't want anything bad to happen to them, to any of them. And so then you get all these advertisements for, hey, this is the way that you can make sure your baby sleeps safely. And it's like, oh, I probably need that. But this is a sort of tool that I think that they're not very good. Not that they're ineffective, but it's the sort of thing that if you get a notification, either it's fallen off or it's a kind of a bad state to be in to begin with. Okay, so anyway, back to the structure here. These are histidines. Now, on this side, these kind of like not olive, but I don't really know what that color is. Those are, I believe it's a phenylalanine and another amino acid. I just want you to look at this and not get thrown off by what is there. Now, when it comes to what are the critical amino acids for positioning iron in the center of a heme ring, I want you to know it's histidine. There's a distal and a proximal histidine. One histidine that basically coordinates the positioning of that iron ion, and then one that kind of makes O2 squeeze in a certain direction in a certain way. Now, oh, I'm getting a free coffee delivery. Thank you very much. Um, so with that in mind, let's go on to this next slide. So this next slide is talking about our protein structure and ligand binding. Sorry, might you repeat histidines? Thank you very much. Yeah. These histidines, what they're important for, I'm going to erase some of this. We've got histidine helps position Fe2 plus within the ring, within the heme ring, and so that would be your yeah, and basically helps position or helps no let me see helps let me see let me makes the correct space for O2's, I'd say binding insertion. I'm going to go with binding. It just makes the right spot for that O2 to bind to. Now, I'm going to go on to the next slide, but then I'm going to come back because that point is an important point. I was talking about those histidines, and those histidines are important. Now, this whole slide right here is about ligand binding, so about the O2 binding, but it brings up an important and interesting topic. So, if you have gas utilities where you live, chances are you have a CO or a carbon monoxide detector. If you have gas utilities and you do not have a carbon monoxide detector, you should probably get one. Now, the reason for this is one, carbon monoxide is odorless, so you can't smell it. It's not like a propane leak or anything like that. You can smell those. Um, Carbon monoxide is not, you're not going to be able to detect it or notice it without a carbon monoxide detector. Now, this first bullet point here says that KD, so the dissociation constant for carbon monoxide is 20,000 times smaller than the KD for O2 for unbound heme. Okay, this unbound heme. What does that mean? That means if you were to isolate heme plus the Fe2 plus. If you're to isolate that and you exposed it to CO and O2, this isolated heme Fe2 complex is going to prefer to bind carbon monoxide. Basically 20,000 times stronger or a greater affinity that it has for O2. Okay. Now, you might say, "Oh, that's pretty shocking." It is. It is. You might also look at that and say, "But wait a minute. You're talking about unbound heme. Well, how relevant is that physiologically? How much does that relate to heme as a part of hemoglobin? Does it relate? It does, but it does relate and it is significant because if you are to use bound heme bound to MB or myoglobin, you would see that the KD for carbon monoxide is 200 times smaller than the KD for O2. So a fair question there is when you compare these two things, or a valid point would be to say, well, the presence of the protein, and I'm just going to go ahead and label it as MB, the presence of myoglobin alters CO binding to the heme. Could everyone give me a one if they understand that point? This one that I'm putting the stars by. Okay, great. Now, what I'd like you to take away from this is that, well, the presence of the protein drops that by, what would that be? 100x? It's 100 times, or it has 100 times lower affinity for carbon monoxide in the presence of myoglobin than in the absence of myoglobin. Absolutely. So think about this as if we've got this situation, and then myoglobin, MB plus heme plus Fe2 plus. And you exposed it to carbon monoxide and O2. So I can give you scenario number one up at the top. Scenario number one is that you have extracted heme and iron. Though that complex, that heme iron complex, just the heme ring with the iron in the middle of it. And you've got a mixture of carbon monoxide and O2. You got the mixture of those two gases. What this heme Fe2 plus complex is going to do is it's going to bind to carbon monoxide 20,000 times stronger than, or maybe you could think about it statistically, it's going to be that much more likely to bind to carbon monoxide than O2. Now, scenario number two, by comparison, if you gave myoglobin, the oxygen binding protein, plus heme, plus Fe2 plus, so you basically reconstructed myoglobin in a physiological sense, and you gave it both carbon monoxide and O2. What's going to happen is it's going to have a preference for carbon monoxide, but it's not going to be as dramatic as in the absence of myoglobin. So it's going to still have a preference for carbon monoxide. It has that affinity, a greater affinity for carbon monoxide than O2, but we're talking about a KD 200x smaller compared to up here where the KD is 20,000x smaller. Absolutely. So the takeaway from this part as kind of like a physiological or like I guess kind of a safety consideration is it's good that we have hemoglobin and myoglobin. Because if we just had free heme floating around in our body and that molecule alone transported oxygen, well, it's going to be able to pick out carbon monoxide so much better than, or sorry, if we just had heme, that would be able to pick out carbon monoxide in a mixture of O2 and carbon dioxide. So O2 carbon monoxide and carbon dioxide, you'd be able to pick out the CO so much easier. Now, this number kind of reflects like, hey, it's not as extreme as this, but any exposure to carbon monoxide is potentially fatal because it will outcompete for this spot, this binding spot. So in the event that you have like a small amount of carbon monoxide can be fatal, and it is fatal. Okay, so now I want to come back here. And what I want to, oh, I'm sorry. Let me, captions. Sorry about that. Um, so I want to come back here and talk about this. We've been stressing Fe2 plus, and that is absolutely important. Fe2 plus versus Fe3 plus. Now, the difference between these is that, well, Fe2 plus and Fe3 plus, what's the difference? One electron. Now, with that said, though, if you think about Gen Chem 1, and you remember Gen Chem 1, there's some of the things that you learned about the organization of the periodic table, you learned about, uh, let's see, trends, periodic trends, you learned about ionization energy, Fe2 plus versus Fe3 plus. What's the difference between these in terms of their size? Well, Fe3 plus has one less electron. So by it having one less electron, it's going to be smaller. This is going to be smaller than Fe2 plus. Now, I bring that up because if you think about a heme ring, and I'm going to draw a very rough model of a heme ring. Yep, it's getting rougher as the seconds go by. Sorry about that. Fe2 plus. We've got these little bonds where these rings are kind of being held together in this particular position by that iron ion. If you have a smaller iron ion in there, that's going to pull those rings even closer. So the structure of that heme is going to be a little bit different. Now, that is going to lead to, if your iron gets oxidized to Fe3 plus, that's going to lead to your heme complex being kind of colored brown. And this is going to lead to a condition known as methemyoglobin. Now, this is something that people can live with. It is, I think that you probably have um, overall, your life expectancy is a little bit shorter because your body's not moving as much oxygen, or it's less effective and less efficient at moving oxygen around. Now, this is also like there's some people, I had a friend who did his undergrad at the University of Kentucky, and he told me about the blue people of Kentucky. And I'm just going to label it as Kentucky. This wasn't like, oh, they're super pumped about Kentucky basketball. That's why they're the blue people. But instead, it's because they've kind of lived in a very isolated community, and they have these kind of genetic traits that get passed down generation to generation. And one of those traits is they largely have the affliction of methemyoglobin, and they have a little bit of a blue hue to their skin. Okay, and so that's where the nickname of the blue people of Kentucky is. So this heme complex combined carbon monoxide, NO, H2S, those are all capable of binding there, and therefore they are all capable of um, replacing that O2, which is why they are all potentially toxic. Now, the biggest threat there is that carbon monoxide. These other two, man, H2S, you know when you've made that, it's got a solid stink to it. But carbon monoxide and NO, carbon monoxide, it's going to have no odor, so it's going to be a little bit more hazardous. Okay. Now, with that in mind, the point is the Fe in the heme structure 2 plus or just Fe? Oh, the kind of preferred, I'm going to write it right here. It's 2 plus. The ideal oxidation state is that iron 2. So iron, I'll put 2 in parentheses. Iron 2 is what you want. Okay. Now, oh, and sorry. Last thing was, so I always like to bring this up, and I spent a little bit of time on this, maybe more than I have in the past, but all of this right here, it's all spatial awareness or spatial importance. All of these different amino acids, that histidine, this phenylalanine, this histidine, this valine, they're all positioned in a certain way for an optimal kind of insertion of this O2. Now, if this right here, rather than a valine, were some other amino acid, like an alanine, would this still, would you still be able to bind O2? Yeah. Would it behave a little bit different? Potentially. If histidine E7 were mutated to a different amino acid, rather than histidine, maybe this were, let's say, a, let's go with a glycine. If it were a glycine as opposed to a histidine, do you think that O2 would be as likely to bind here? Not really. Because let's think about histidine. Histidine's a nice ring and it's got a lone pair of electrons, an LP of electrons. Does glycine have that? Nope. In which case, are we going to have, if it were mutated to a glycine, would we have this kind of stable spatial construction? No, we wouldn't. So a mutation like histidine to glycine to this specific histidine would be potentially problematic. And maybe that would lead to, well, now carbon monoxide can bind much more effectively. So when you think about amino acids, I think that it's good to think about how they're classified. Are they polar? Are they non-polar? But then also think about their geometry. And I'm not saying it, I don't want you to be thinking like, oh, now I've got to remember trigonal bipyramidal. Don't stress about that. But instead think about what is the space of that? Well, this right here, that's a five-membered ring. Is a five-membered ring going to occupy the same space as a methyl group? No, it's not. Is a five-membered ring going to occupy the same space as a, I don't know, a two ring structure like tryptophan? No, it's not. So I just want you to kind of be thoughtful of that. Okay, now let's proceed. We've used hemoglobin as our model, but it is just that. It is a model. Hemoglobin and myoglobin are models. Lots of what we're going to do as we begin to quantify this is going to be also relevant for enzyme substrate binding. So I want you to be comfortable with these terms. P for protein, not too much of a stretch. L for ligand, and PL for the protein ligand complex. So pro lil lig complex. Now, the dissociation of the protein ligand complex. So as this thing falls apart, we can write it as an equilibrium. Just like we did in Gen Chem 2, where we learned about equilibriums, where we had the concentration of our products over the concentration of our ligands. Or not our ligands, our reactants, sorry. So what we've done is we've taken reactants. Reactants, products. So that will give us a KD, or dissociation constant, where we're just looking at a ratio. What is the ratio of a concentration of our products over the concentration of our ligands? Now, in most conditions, the ligand concentration is very large compared to the protein concentration. And in this case, whenever I say protein, I'm referring to this as, or I'd like you to also think about this as the free protein. So the free protein, it's not bound to anything. It's just a second. There we go. Therefore, the formation of PL does not appreciably change the L concentration. So what that means is that as the protein ligand concentration goes up, as PL goes up, L, sure, it goes down, but it doesn't plummet. You're making a small kind of dent in the amount of L. Okay. Now, we're going to take this and we're going to build on this over the next few slides. when it comes to ligand binding math, we use this number, this fractional percent of ligand binding sites. Okay, so we use this theta right here. If you have a protein, I'll use here's my model protein. And these two kind of indentions there and there are my ligand binding sites. Okay. Now, if I have, I'm going to go ahead and change colors and I'm going to say, all right, well, here is that. Okay, so I've got one copy of my protein and I've got one binding site occupied. So you could say that 50% of my ligand binding sites are occupied. That's essentially what we're trying to look at, or that we are looking at when we look at this theta right here. Now, PL is the protein ligand complex. Free P is the protein without any ligand bound. And then again, PL is the protein ligand complex, with the number on the top being the number of binding sites that are occupied divided by the total number of binding sites in solution. So if we were to look at this protein model right here and fill in theta for this, we would say, okay, number of binding sites, 2. Total number of binding sites in solution, or sorry, number of binding sites occupied. I apologize, not 2. I would say 1, because there's one binding site occupied, and I would divide that by the total number of binding sites in the solution. And I would say that's 2. Another view of that is, let's say that we've got, I'm going to go with my classical Pac-Man style enzyme. Now I'm going to get this right here. And I'm going to do one more Pac-Man. Okay, there we go. I'm going to calculate theta. Theta is equal to the number of binding sites occupied. Here, my number is going to be 2 over total number of binding sites in the solution. Okay, now what I'm going to do here is I'm going to take the free P and the PL so that I can come up with that. So how many free proteins do I have? 1. This guy right here. How many protein ligand complexes do I have in my solution? 2. This one and this one. So this is going to give me 2 over 3. Could everyone give me a Z in the chat if they understand this calculation right here? Okay. So as soon as we kind of have an understanding of this theta calculation, and we understand, okay, well, this is our dissociation constant, KD, we can take that KD and plug it in for some of the terms that we see in this theta value, or in this theta calculation. So the dissociation constant, or dissociation equilibrium equation, can be rewritten as PL. So looking at, sorry, I've got some arrows that I'm going to delete. My goal, let me rephrase this, is I want to put things in terms of theta. Put in terms of theta. So I want to think about dissociation constant. I want to think about theta. So what I'm going to do is I'm going to say, all right, I want to put it in terms of this PL, which I like this, divided by P plus PL. So how am I going to do that? Well, I've got PL right here, PL right here, and I've got this dissociation constant. I'm going to do the algebra to rearrange this. So I'm going to multiply each side by PL. So now I've got PL, concentration of PL times KD is equal to PL, PL. Now I'm going to divide each side, or sorry, yeah, that's right. No, it's not right. I don't need that one anymore because those canceled out. I apologize. So I've got PL times KD is equal to P times L. I'm going to divide each side by KD, divide each side by basketball superstar Kevin Durant, and I'm going to end up with PL is equal to P times L divided by KD. Now what I can do is take this value for PL, this whole thing right here, and plug it in here, and plug it in here. And when I do that, what that enables me to do is kind of simplify my equation and simplify my equation down to this right here. I've done this substitution here and here. So this was what I just did the legwork on. And now that I've done that, I've got this equation right here. P is going to cancel across the board. Then what I'm going to have is effectively the concentration of my ligand over Kd plus the concentration of my ligand. This equation allows us to express the fractional percent of our ligand binding sites occupied as a function of our ligand concentration. The reason for this is if you think about protein ligand complex, well, that's very transient by nature. It's going to be there and then it's going to be gone. Ligand concentration is something that we have a little bit more control over. We know how much ligand we added to our reaction, so we can study that a little bit more easily. Now, when it comes to applying that, so like I said, this is all a model. This is the math that we did leading up to it. We're going to ultimately graph it. We're going to get a hyperbolic curve. So I'll show you those curves in just a little bit. But we want to take this protein ligand modeling and apply it to the model that we have, our oxygen binding proteins. How does the binding of O2 to myoglobin vary with oxygen pressure? Think about this as oxygen pressure. That's similar to the concentration of O2. Now, concentration of O2, we don't really quantify gases like O2 that way because we can use Charles's law, or we can, put this in terms of Charles's law and say, okay, well, the quantity of gas or the concentration of our gas absorbed by a liquid is proportional to the partial pressure of the gas above that liquid. So when we look at a graph for this, what we're going to see is the x-axis is going to be partial pressure of O2 because that is effectively the same as our ligand concentration. Okay, we've been on a little bit of a journey. Could everyone give me a 5 if they're like, yeah, this has been a journey, but I'm still with you, or a 9 if I lost you on the last slide? I'm not done with this slide yet. Okay. All right. So now what we're doing is we're looking at O2 as our ligand for myoglobin and for hemoglobin, but we're going to start out with myoglobin. Why? Because myoglobin's simpler. Simply put, myoglobin is simpler because of the fact that myoglobin only binds to one O2 molecule. So we've got MbO2. This is equivalent to PL. That's our protein, and that's our ligand. It doesn't matter that it's O2 because O2 is a molecule. That's what it's bound to. Okay, so I'm going to erase this just so I can eliminate, the markings that I have on this page. Myoglobin, or Mb, is our free protein. O2 is our ligand. So I can rearrange this to make my Kd expression. The concentration of free myoglobin times the concentration of O2, our ligand, divided by MbO2. That is our Kd. Now, from here, what we need to do is account for Charles's law. Charles's law says, well, we don't really look at gases in terms of concentrations or molar concentrations. So we're going to sub that out. And we're going to say partial pressure of O2, or PO2. Okay, easy switch there. Done. Now, this is our way of understanding how much O2 our protein is going to bind, how much our ligand, how much of our ligand our protein will bind. Now, this is again our PL, P, and L. We use Kd to express affinity of a protein for a ligand, in this case, oxygen. Now, mathematically, our Kd, our dissociation constant, is the inverse of our association constant. So what that means is that the lower the Kd, higher the affinity of the ligand to the protein. So if you have a Kd that's something like 0.1 versus, let's say, protein A and protein B, 0.0001. And I'm going to go ahead and put these in terms of nanomolar. Which protein has a greater affinity or binds to the ligand more tightly? Is it protein A or is it protein B? The lower the Kd, and these are the Kd values. Well, if our Kd is 0.1, okay, I'm going to turn the annotate for everyone off. Clear all drawings. I think I turned it off. Well, between these two proteins, protein A has a Kd of 0.1, protein B with 0.001. Protein B's affinity is going to be higher because it has a lower Kd value. So I'm going to write that out. Lower Kd means higher affinity. Okay. Now, I think lots of this will make a little bit more sense as soon as we start graphing it, which if you're looking off to the left, you'll see that's not a long time. So what we look at is this theta value, which is our basically our percentage of those binding sites that are occupied. Now, another way of putting that theta, so theta is related to protein ligand complexes. If we wanted to apply that directly to our model of oxygen binding proteins, we use this term right here, Y. Y is the number of binding sites occupied divided by the total number of binding sites in the solution. So this is using the same calculation up here, but applying it directly to oxygen binding proteins. You might think, oh, well, that's kind of excessive. You're not really wrong. But when we look at these graphs, I want you to recognize that the y-axis is going to be labeled with a y, not because it's in identifying the y-axis, but instead because it's looking at the fractional percent of those O2 binding sites, or basically percent saturation. Okay. Now, when we do this for myoglobin, we're ultimately going to come up with a y is equal to PO2 over KD plus PO2. Remember, this is our O2 concentration. And this right here accounts for how tightly does our protein bind to that O2. Now, what an oxygen binding curve for myoglobin looks like is shown right here. This curve right here is our hyperbolic curve. This hyperbolic curve, what I want you to, that's the shape of this curve. What I want you guys to be familiar with is the y-axis as well as the x-axis. The first point is our y-axis explains the percent of myoglobin's proteins, or MB, saturated with O2. And then our x-axis represents, well, for lack of a better term, the concentration of our ligand or our partial pressure of O2. So what this is showing is this curve is representative of lots of data, lots of different experiments. And whenever I say different experiments, I really just mean added trials. So this curve right here shows, okay, well, here's a trial, 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 here's a trial. Doom, 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 doom. Okay. Now, my question for you guys is along the y-axis. Think about this as the same as 100%. And then this at the bottom, 0%. So if we were down here, that would be there are no MB proteins with O2 bound. Could everyone give me a Y or an N if they understand this point right here? Okay. And whenever we look at any sort of graph, we're kind of playing a game of kind of playing a game of battleship. So we've got our coordinates. So what concentration of O2, tell me this, what concentration of O2 gets us to a fractional percent saturation of 0? How much O2 do we need in the reaction chamber to have no myoglobin bound to O2? Well, 0. Perfect. Great job, Miles. Okay. So my y coordinate is 0. My x coordinate is also 0. Could everyone give me a 5 if they follow that, or a 7 if they don't really follow it for that example? Okay. Now let's take it the next step. At what concentration would you say, I'm going to go over here. What O2 or partial pressure of O2 are, let's say, 85% of proteins saturated? And so to answer this, you want to start on your y-axis. And we want to go up that y-axis. And if this right here is 100, call that about 90. And let's call this about 85%. So our y coordinate is that 85. That's what we were looking for. And now we're going to kind of extrapolate outwards. And you might arrive at a slightly different number than me, but 20-ish, I can work with that. 14-ish. Yeah, I think that there's kind of a broad range that people are gonna work within, but something, you know, that's not a really straight line for me. I'm sure that there's somebody who got a piece of paper and they're like, aha, there. Could everyone give me a 9 in the chat if, okay, I understand how to do that? Nice. Okay. Now, what about 100%? How much O2 would you need to add for this protein to be completely saturated with O2? Or maybe is it something that it's probably not going to be 100% because the purpose is this protein to bind O2 and release it? Sammy, Jackson, spot on. It's not really going to attain that perfectly. It's not going to reach 100% saturation. So this graph, I think, is kind of a good graph because it shows you that, hey, at some point, whether you're at 25 torr, remember, you got to think about units of gases, 25 torr of O2 or 30 torr of O2, the difference between these is very minor. If we were to extrapolate this out to go to, 75 torr, it might not change that drastically. Sorry. Now, what is an important point for us is known as the P50. P50 is where half of the protein is saturated with O2. Could anyone make an estimation as to what the partial pressure of O2 is that will get us to half of our protein saturated? And that P50, think about 50%. So remember, our y-axis is going to be our percentage. So we're looking at it right about there. Sammy brings in the 2.5, spot on, about 2.5. So at about 2.5 torr, half of our myoglobin proteins have O2 bound. This is our P50. Now I'm going to go on to the next slide because this is a significant number when it comes to oxygen binding proteins. P50 is kind of your barometer for comparing different oxygen binding proteins. So a high P50 indicates low affinity for O2, and a low P50 indicates high affinity for O2. And I want to kind of present some options for you. Hemoglobin for adults versus hemoglobin or fetal hemoglobin, they have different P50s. The proteins are very similar to one another, but they have different P50s. Now, when our partial pressure of O2 is equal to our KD, then 50% of the ligand binding sites are occupied. Myoglobin, this is true for myoglobin, this is true for hemoglobin. It has to do with how many of those binding sites are actually occupied with O2. Now, with that in mind, one thing I want you to remember, and this tends to be a this tends to trip people up from time to time, and that is what are the units for P50? And what I've found is that people over the years, they hear units for P50, and the first thing they think is it percent? They get a little bit mixed up on that because they see a graph like this and they're like, oh, okay, P50, got it. It's where these two lines intersect. And they kind of lose sight of that y-axis. Remember that the P50 is the point where half of the protein is saturated, and your y-axis is your percent saturation. So as soon as you say, well, P50 or 50%, look at that y-axis and then say, how does that relate? So in this case, the units for P50 are going to be in torr. And you're absolutely right. It's going to be torr. Okay. Now, I wanted to go through all of this because graphically, enzymes look very similar to oxygen binding proteins. There's parallels. The difference being, well, an enzyme doesn't bind and then release something. It binds it, catalyzes a reaction, then releases the products. There are enzymes that are going to have graphs that look very similar to this right here. But what's going to differ is it's not going to be a question of is it saturated, but instead the rate at which something is being done. So we're going to go on now to change or to pivot a little bit and talk about enzymes. Now, we talked about enzymes as a model, and actually, I'll get a drink of water. Can you give me on a scale of 1 to 3, one being I feel pretty good about oxygen binding proteins and their graphs and P50, and three being, hmm, I might have to watch that whole lecture again at 0.25x speed. All of office hours on Thursday, 12:30 to 1:30. If the link's not on the Canvas page, which I thought I put it on there, but maybe I didn't, it's on our, and I'll make sure that it's on there, first of all, but it's also on our blah, 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 syllabus. Okay. Okay. So enzymes. Think about an enzyme as this is your protein. This is your biological molecule. And I know that I mentioned last time that not all proteins are enzymes and not all enzymes are proteins. And well, there are enzymes that are not proteins. But let's go with this as kind of our simple model. This would be a bi-substrate reaction where we got two different substrates, substrate A and substrate B. And our enzyme, represented as the letter E, is going to form a complex, the ES complex. Now, in this case, yeah, we've got two substrates indicated, but we didn't say like ESS or anything like that. So this ES is just saying that both of the substrates, or if it's an enzyme that only has a single substrate, that is bound. Now, ES star or an asterisk, what that indicates is that the enzyme changes and there is a reaction between substrates A and B. Or if it's just a single substrate, that single substrate has undergone some sort of change. Now, we have resulting from that a complex of the enzyme and the product, or EP. This is the EP complex. So we have E plus S yields reversibly the ES complex, which reversibly forms the ES star complex, which then leads to the formation of our enzyme plus our product. And then you guessed it, folks, E plus P, because the enzyme and the product are going to dissociate. Now, we talked about models like the sequential or the ping pong model. Those all can kind of be comported into this. There's some subtle differences, but this overreaching model is applicable to all of those. Now, those products, whether it's C and D or whatever, are going to be released. E plus P indicates that the enzyme has released the products. The enzyme is ready to go again. It's ready to bind more substrates and catalyze the reaction again. Here's our kind of flow chart of all of that in the sequence. What is taking place? The free enzyme and the free substrates. The substrates bind. A reaction takes place. Product is formed and the products are released. Now, what we're most interested in when it comes to an enzyme catalyzed reaction is we want to know about the product and the formation of that product. Now, when we talk about any sort of chemical reaction, we're interested in rate constants, the forward and reverse rate constants for the formation of the enzyme substrate complex, as well as the dissociation or the kind of deformation or breakdown of that enzyme substrate complex. So as soon as you form that enzyme substrate complex, it could go back to the free enzyme and the free substrate, or it could go forward to the free enzyme and the free product. Now, when it comes to studying enzymes, there are two big names in enzyme kinetics. One is Maud Minton, and I cannot remember Michaelis's first name. These are two biophysicists back in the late 1800s. I believe they worked at McGill University in Montreal. Um, and what they developed was this study of enzymes and study of product formation and basically the flow of everything that's happening when it comes to an enzyme catalyzed reaction. And we're going to look at a series of graphs related to enzymes and substrates and enzyme substrate complexes and all of that. But this first graph, what I want you to recognize is our y-axis is showing our relative concentration. The x-axis is the time that's taking place. So at our time point 0, That is where our substrate concentration is the absolute highest. It's at 100%. The free enzyme is also at its absolute highest. Now, what is going to happen is as soon as you start this reaction, or as soon as you start the timer, the substrate and the enzyme represented by this blue dashed line, the substrate represented by this black line, the two concentrations or those two concentrations will both drop. And I'm going to use a good SAT vocabulary word, precipitously. I feel good about that. Those two are going to, and I'll use more of a Joel type of word, those two are going to plummet. So the substrate and the enzyme concentration are both going to plummet very quickly. What is going to increase at that same time is this enzyme substrate complex, denoted by this dashed, I don't know, kind of olive colored line. It's like a faded olive, though. Then the product, our free product, the concentration of our product is going to lag behind that a little bit, but that is slowly but surely going to go up, and that is only going to go up. So, what I want you to see and what I want you to take away from this is that your substrate's concentration is going to go down and it's only going to go down. The rate at which it's going to go down is going to be very fast at first, but then it's going to kind of not become linear, but a little bit more linear. The rate at which it's dropping is becoming a little bit more linear. So then our enzyme, our free enzyme, well, that's going to drop, and then it's going to be it's going to increase very gradually, almost at the same curvature, but inverse as the enzyme substrate complex. The product, the free product, is going to go up and it's only going to go up. So think about this as the substrate is going to go down and only go down. The product is only going to go up because the substrate is basically replacing the product. The enzyme substrate complex, by comparison, well, that is basically, that's a placeholder almost, because as soon as you've consumed all of the substrate, are you going to have any more of the enzyme substrate complex? No. Now, notice the enzyme substrate complex doesn't go to absolute zero. The substrate complex is shown to go to zero, but you're going to reach an equilibrium. Where the enzyme substrate complex, there's going to be a very small amount of that. And there's going to be a very small amount of the free product, or sorry, a very small amount of the free substrate, and most of it's going to be converted into the product, all depending on kind of the equilibrium constant there. So our substrate is going to be replaced by our product. Our enzyme is going to, in part, be replaced by the enzyme substrate complex, but then it's going to kind of regain its footing. Okay, so could everyone give me a 9 in the chat if, okay, I track all of those and I follow what's happening. And then a 2 if, I'm mixed up by one or more of those. Okay. All right. Now I'm going to jump ahead to this slide right here because that was all a run up to this slide right here, a run up to this. Sure. So I'm going to, yeah, I'll go back here. So our substrate, our free substrate, the concentration of our free substrate is going to go down. That is effectively going to be replaced by our free product. So if you think about this as E plus S, and I'm going to leave out the ES star plus P. Okay. This right here, oh, that's a bad color to highlight that. Yellow is a good one. So the S is going to basically be replaced slowly but surely through this process by the P. Substrate concentration goes down, product in turn replaces that. Next up is, okay, so that's those two. Now the enzyme substrate complex. Look at this, equilibrium arrows. The enzyme substrate complex can go in either direction. It can go this way or it can go this way. Now, if you look back here, where did I have it? I had it. Could have sworn that. No, never mind. Disregard what I was saying. Oh, here it is. Sometimes you will see, I'm going to erase some of my markings. Sometimes you'll see the enzyme substrate going in a single direction towards the free enzyme plus the free product. You'll see that. Is that the most accurate thing? Not really, because of the fact that um, it is at equilibrium, or there is an equilibrium there. So this E plus P can go back to the enzyme substrate complex. Is it likely to? No. And that's the kind of loophole that people use. And they're like, hey, this is unlikely to go back to this. So we can get away with a single direction. Now, back to the point here. The point is, we've got our ES going back to E plus S. ES could also go forward to E plus P. So that's why we have a small amount of the ES complex that persists here. And at the same time, our enzyme concentration starts really high, and then you can't even see how quickly it drops off. And eventually it's going to reach an equilibrium, and the free enzyme concentration is going to remain there. Okay, hope that was helpful. Now, when it comes to this Michaelis-Menten kinetics, what we are most interested in is the steady state, this range, not after it immediately takes off. This is what's known as pre-steady state kinetics. We're interested in the steady state kinetics. We're interested in this region of our substrate concentration where the drop is a little bit more linear, where we can kind of track it a little bit more easily, where it's a scary roller coaster, not a terrifying roller coaster. So that's where we want to live when it comes to enzyme kinetics. Now, that enables us a mechanism to track the product formation, denoted by the red line, our free enzyme and our free enzyme substrate concentrations, because those are relatively constant, and our substrate concentration, our substrate consumption. Now, when it comes to understanding this, what we have are a couple of different models. We have our enzyme, denoted by these oblong Pac-Man figures, and our substrate, denoted by these red balls. Our substrate and our enzyme here we have kind of an imbalance. Lots of enzyme, not much substrate. So in this situation right here, is it going to be difficult to convert that substrate into a product? Not at all. Because let's look at these enzymes. If these enzymes, where I'm putting the X, are working as hard as they possibly can, they're going to grab the substrate, convert it to a product. They're going to have no problem because this enzyme right here is going to be able to grab that substrate, make a product. Done. This enzyme right here, this enzyme right here, this enzyme right here, they're all kind of waiting around. They don't need to do anything at the moment. They're not like, oh, well, if only we had more substrate. Okay. Now, this middle ground here. This middle ground shows, the number of substrate remains the same. 1, 2, 3, 4, 5. Or sorry, our enzyme remains the same, but what happened to our substrate? Our substrate went up pretty dramatically. And you know what? This is almost the place where our enzyme is it's close to meeting its match. What about this far side over here? And this far right side, it's not a matter of, oh, we have too much substrate. Instead, we just have a large amount of substrate, high substrate. So converting substrate to product, well, your enzyme's it's working as hard as it can. And in this case, let's take situation A and situation B. Let's imagine that for the enzyme to bind the substrate and release the product, let's say that it took, 5 seconds. It's going to bind it, release it. Takes 5 seconds. If you gave situation A 10 seconds to work, do you think that all of these enzymes working together could bind those substrates and create product? Give me a Y or N in the chat. Okay. Now, same thing over here in situation B. You give them 10 seconds. Do you think that all of these enzymes could bind and release, bind the substrates, release the products in that 10-second time frame if it takes them about 5 seconds to do that each one? And you might look at those numbers and be like 1, 2, 3, 4, 5, 8, 9, 10, 11, 12, 13, 14. Ooh, it's going to be close. Because if each one of those enzymes binds to the substrate, releases, and there is about 19, I don't think it's going to be able to do that. So I would describe this situation as, well, you saturate the enzyme with substrate. You saturate the enzyme with substrate, and you give them this fixed time interval, about 10 seconds. Would you agree with me? Give me a Y or an N. There will be excess or unused substrate. Yeah, we're going to have excess substrate. Are these enzymes still working as fast as they possibly can? Yeah, they are. But there's going to be excess. Now, I want to show you this graph right here. Well, yeah, I'll go with this one. These enzymes are working as fast as they can, but the substrate concentration is too high. So it's kind of like this high substrate situation right here is a good way to test what is the enzyme capable of. That's where we get the what's known as our first important kinetic parameter known as a Vmax, the maximum velocity that the enzyme can catalyze the reaction at. So Vmax, I'm going to say maximum velocity that enzyme can catalyze lies reaction. Right. Okay. Now I'm going to go on to the graph. Because what I want to do, I'm going to jump ahead. I'm going to jump ahead to this graph. The reason I'm jumping to this graph is because what I want you to do is look at the y-axis. Our y-axis is our reaction rate, similar to velocity. Substrate converted to product. Our x-axis is our substrate concentration. These two axes, our y-axis and our x-axis, I want you to think about these two as being similar to our oxygen binding curves. Our y-axis, I want you to think about that as percent saturation. This being the Vmax for an enzyme or equivalent, let me erase that. This point right here being equivalent to a saturated myoglobin. Does that make sense? Could everyone give me a 5 in the chat if they understand that connection? Or I'm saying an enzyme is doing everything it can. It reaches its Vmax. An oxygen binding protein like myoglobin, when it's 100% saturated, that's where it's kind of maxed out. Okay, awesome. Now, what was our important kinetic parameter? Our important kinetic parameter for our oxygen binding proteins was the P50. Could everyone give me a W if they see on this graph something that looks, maybe some notes or markings on this graph that looks like what we saw for the P50, how we denoted the P50? Yeah. We looked at kind of halfway down our y-axis right here, and then we extrapolated out, and then we drew a point down. This would be the P50. Now, for an enzyme, this is known as the Km. And I know it's 4:50. I'm just going to finish this statement, then I'm going to let you guys down. We're going to pick this up again on Wednesday. The Km is to an enzyme what the P50 is to an oxygen binding protein. Okay. So the P50 is measured in terms of partial pressure of O2. What amount of O2 got your protein 50% saturated? For an enzyme, we say, how much substrate? How much gets your protein? Let me rephrase that. How much substrate gets your enzyme to work at half of its max velocity? Okay. I'm going to stop right there. I know cliffhanger sort of thing. I apologize for that. We'll pick this up again on Wednesday. I want to say thank you so much for your time. Thank you for your attention. Thank you for your participation. You guys are doing a great job. I hope that I'm doing as well as you guys are, but that's your perception. So, um, if there's anything that comes up, let me know. I can probably try to meet you tomorrow. Other than that, though, I hope you guys have a great evening, and I will see you guys on Wednesday.